Hey Wheaton North, Mr. Yergler here. Let's talk about redox reactions. A redox reaction is a reaction that involves the transfer of electrons, at least one electron. So there's several examples of this, all kinds of examples in the human body and in biology. Really complex reactions. There's a lot of redox reactions happening in there. Rusting of metal is a redox reaction, and then batteries are also a redox reaction. The term redox comes from the combination of reduction and oxidation. So there's two things going on at the same time, and they always take place simultaneously. The way I remember this is to always use the phrase oil rig to remember which one is which. So oxidation is loss and reduction is gain. Put a star next to this. We're talking about electrons. So losing electrons is oxidation. Reduction is gaining electrons. Let's look at a few examples. If sodium transfers from solid sodium to ionized sodium, it's losing an electron because it forms a positive one charge. That loss of an electron means that it's getting oxidized. If we look at chlorine, it's gaining electrons. It goes from neutral to -1. So that's reduction. So in this case, sodium is getting oxidized and chlorine is getting reduced. This picture is great because it shows that these are all happening at the same time. If one substance is getting oxidized, it's losing electrons, right? Oxidation is loss, and those electrons are going to the thing that's getting reduced because reduction is gain. So you always have oxidation and reduction happening at the same time. We're going to talk about things getting oxidized or things getting reduced. We're not really going to use the terms reducing agent and oxidizing agent. It adds another layer of complexity to it, and it's not really necessary. In any redox reaction, there's usually going to be a change in charge, almost always. There are cases where you won't really see a change in charge, but there will always be a change in oxidation number, and we'll talk about that in a second. Here's our examples from the previous slide. If we put them together, if we combine sodium and chlorine, we have a full reaction. So these are actually what we call half reactions, the oxidation half reaction and the reduction half reaction. So we're showing that sodium is losing an electron and chlorine is gaining electrons. And notice that because sodium loses only one electron, that's why we have to have a 2 in our balanced equation, because you can't gain 2 electrons if sodium is only losing 1. This half reaction is actually happening twice every time this reaction is happening. Put them together and we have our normal molecular reaction that we're used to seeing. All right, oxidation numbers are used to keep track of electrons during a reaction because we need to be able to identify what's losing electrons and what's gaining them. It's similar to charge, but not always the same, and so we want to follow these rules. Elements, meaning things that don't have a charge, like copper, chlorine, oxygen, they have an oxidation number of 0. Monoatomic ions, the oxidation number is equal to this charge, so it's the same thing. So this has an oxidation number of +1. Fluorine is always -1. Oxygen is always -2. There's a few exceptions to those. Hydrogen is almost always +1. And the sum of the oxidation numbers has to add up to 0. Unless it's a polyatomic ion. If you have a polyatomic ion, anything that has a charge overall, we're going to add up to that total charge. Let's look at a few examples. Assign oxidation numbers to the following. So iron +2, what would its oxidation number be? We want to look at rule number 2. This is a monoatomic ion, and so the oxidation number is just the same as its charge, and so it's +2. What about sulfur? Sulfur is just an element. There is no charge on it, so it's just elemental sulfur, and so it would have an oxidation number of 0. What about oxygen -2 ion? Again, this is a monatomic ion, and so it's going to be just -2. And chlorine, again, number 1, this is an elemental substance, and so it's just going to be 0. What about if you have a compound? So let's figure out the oxidation number of nitrogen in sodium nitrite. Where do we start? Well, we know that oxygen almost always has a -2 charge, and so we can figure that out, and there's 2 of them, so that makes it -4. We know that the sum of the oxidation numbers has to add up to 0, right? So we can kind of figure this out algebraically. Sodium is always going to be a +1 because this is an ionic compound, and so what we really have is nitrite ion and the sodium ion. So that's +1. So from there we can figure out that nitrogen is going to be +3. Whenever we have a redox reaction, one substance is going to increase in oxidation number and one substance is going to decrease in oxidation number. And we need to be able to keep track of which one is doing which. And this is always going to happen in 2 half reactions, right? Because there's an oxidation half reaction and there's a reduction half reaction. Again, oxidation is loss of electrons, right? Oil rig. Oxidation is loss, reduction is gain. And so because we're losing negative particles, if you're losing electrons, the oxidation number actually goes up. And if we're gaining electrons, the number decreases or it gets reduced. Here's our steps to follow our balancing redox reactions. We should have these written down just like we wrote down the ones from assigning oxidation numbers. So go ahead and pause the video and write these down. All right, let's look at an example. I'm just going to follow these steps literally word for word. So let's start with assigning oxidation numbers. We know that oxygen is -2, and there's 7 of them, so that would be -14. The whole thing has to add up to -2, and so what we need from the chromium is a total of +12, right? +12 minus 14 would give us a -2. And since there's 2 chromiums, chromium has to be a +6. If we look over here, chromium is by itself, it has a +3 charge, and so our oxidation number is just +3. So chromium is going from +6 to +3. Is it gaining electrons or is it losing them? It's gaining them. If we look at chlorine, chlorine's going from -1 to 0. Is it gaining electrons or losing them? It's losing electrons because it's getting more positive, right? It has an extra electron here that it's losing. And so our reduction half reaction is our chromium, and our oxidation half reaction is our chlorine. Now we need to balance these. So we've done the first 2 steps. Now that we have the half reactions, for each half reaction, we need to balance elements other than oxygen and hydrogen. So here, if we look at this, we have 2 chromiums, and so we need to balance that out, 2 chromiums. We're going to ignore the oxygen for right now. On this side, we have 2 chlorines on the product side, so we need 2 chlorines on the reactant side. All right, next step, balance oxygens with water. We have 7 oxygens here, and so we need 7 waters on the other side. On this half reaction, we don't have any oxygens, and so we don't need to change anything. All right, next we balance hydrogen with H+. We have 7 waters, which makes 14 hydrogens, and so we're going to add 14 hydrogens to the other side. On this side, again, we don't have any hydrogens that we need to balance, and so we can just leave it alone. If the reactions are basic, add enough OH to each side to balance H+, and then cancel like terms. You'll see on problems, it will say it's in a basic solution or it's in acidic solution. I'm going to do this one as an acidic solution, and so we're going to skip this step. Now we balance charge by adding electrons as either a reactant or a product. All right, this is where you need to really pay attention. We have 14 hydrogens, each with a positive charge, so that's 14 positives. We have -2, so that's a total of +12 on this side. On this side, we have 2 + 3, so a total of +6. So we need to balance out the charge. So where do we need to add electrons in order to balance the charge? We need this side's charge to come down, and so we need to add electrons on this side. 6 negative electrons with our +12 would bring it down to +6, which would match the other side. Over here, we have 2 negatives and neutral, and so we need the 2 negatives. We need to add 2 more negatives on the product side. Now that we've canceled out the charge and balanced the charge, now we need to adjust the coefficients to cancel the electrons. I'm looking at the whole reaction all together. We have 6 electrons here and 2 electrons here. We need to triple this reaction in order to cancel out all the electrons. Because remember, any electrons that we're gaining on one side have to be lost on the other. We can't have that be a different number. So this side is going to stay the same, and this side becomes 6 chlorides, 3 chlorines, and 6 electrons. Now we combine the 2 half reactions. I kind of color-coded this so we can keep track of where everything's coming from. All of our reactants are on the reactant side. Our 3 reactants here are now here, plus our 1 reactant from the oxidation half reaction. And all of our products are together. Our 2 from the reduction half reaction and 2 from the oxidation half reaction. Now we cancel like terms. In this case, the only like terms are the 6 electrons, and so we can cross those off. Your electrons should always cancel. Sometimes you'll have waters on both sides, sometimes you'll have H's on both sides. Anything that you have on both sides you can kind of cancel and simplify. So this is our final total balanced redox reaction. A couple things to keep in mind. This occurs in acidic solutions, so H+ is a reactant, which makes sense. And if it were basic, I mentioned this earlier, we would do the exact same thing, but there was an extra step in the middle. You have to neutralize all your H+ with OH- after balancing for the H's. Okay, so that was a lot of information and a long example, but you need to make sure you have this in your notes because you're going to want to reference it later when we start doing balancing redox reactions. All right, this is Mr. Yergler signing out.